So in this video we are looking at how we can vary a rate of reaction. We're looking at what variables we can use to change the rate of a reaction, i.e. to speed up or slow down a reaction. And we're going to look at why those variables do what they do. So first off, the variables. Well, you can see that we have 4 variables highlighted in purple: temperature, concentration, pressure, and surface area. And we'll come to each of those individually in time. There is one more, which is the use of a catalyst, which we will do in a separate video. So let's have a quick look at what we've got up at the top. We have variables written as a title. So we know we have the 4 variables below, but what we're doing here is seeing how we're going to answer a question on variables. So we need to know a few things. We need to know how the variable affects the particles. Now, these are the reactant particles, if you like. Or you can say reagent particles, that's fine. What we need to know is how the variable affects the particles, because if we know how the variable affects the particles, we can see how the number of collisions per unit time changes or is affected, and therefore we can work out how the number of successful collisions per unit time changes. If you're not sure what I'm talking about with collisions per unit time and successful collisions per unit time, have a look back at the video on collision theory. Let's just run that through. If we know about the variable, we should be able to work out how that variable affects the reactant or the reagent particles, how it affects the reactant or reagent particles, which means we will know what happens to the number of collisions per unit time, which means we'll know what happens to the number of successful collisions per unit time. The per unit time is important because per unit time is all about rate, i.e. how the rate changes. And how the rate changes, which I'll just highlight, can be seen and applied to these rate curves over on the right, which we will talk about just briefly. If we look, this rate curve is amount of product formed up on the y-axis against time on the x-axis. If we are making more product in a shorter time, like we are in the purple line, we're going to have a faster initial rate of reaction. At the beginning, that purple line is steeper and rate is given by gradient. If we look at the green line, it is shallower to begin with, which means that the initial rate is slower. Something is affecting the particles, which means they are colliding less effectively, less regularly, or something along those lines. And that is why we need to look at these different variables. So if we look at the first variable, what's the first variable we've got? Temperature. Temperature is all about energy. What sort of energy? Well, that's important. We need to know what it's doing to the particles. So if we increase the temperature, we increase the kinetic energy of the particles, or the reactant particles. Therefore, and there are 2 bits to this answer, therefore we increase their velocity. Now let's think about what that means. If the particles are moving around with more energy and they're moving around faster, i.e. with more velocity, that means they're going to bump into each other more often. If they bump into each other more often, they're more likely to react. They're also going to bump into each other with more energy, i.e. bump into each other harder, which again also means they are more likely to react because more of the collisions are going to occur with greater or equal to the activation energy. Again, if you're not sure about these terms like activation energy, go back and look at the collision theory video. So let's just run through this in full. Temperature. If we increase the temperature, we are going to be increasing the kinetic energy of the reactant particles, therefore increasing their velocity. This means we're going to have more collisions per unit time, more successful collisions per unit time, and our rate will increase. So if we're looking at this diagram up at the top, the green line would be at a lower temperature, and the purple line overwritten with yellow would be at a higher temperature. One last thing before we leave temperature alone. Temperature, this applies to all states of matter. So that's solid, liquid, gas, solution, all of them. Next up we have concentration. Concentration only really applies to solutions, i.e. aqueous in GCSE terms, because that's the only solution we really deal with. And again, we need to know what's happening with the particles, the reactant particles. How does the variable affect the reactant particles? Well, let's have a look at the little diagram. At low concentration, let's just underline that, at low concentration, it's obvious that the particles are further apart from each other. There are less particles per unit volume. I know it's a 2D picture in front of us, so it's per unit area, but in reality we're going to be dealing with a 3D system, so it's going to be per unit volume. At a higher concentration, we have more particles per unit volume. Let's just write that down. So high concentration, we get more reactant particles per unit volume. If we have more reactant particles per unit volume, we are going to get more collisions per unit time, just because they're tighter in. Imagine you are a load of people running around in a huge sports hall. You're not going to bump into each other very often. If you have the same number of people running around in a very small bedroom, you're going to hit each other all the time, i.e. you're in higher concentration. So, high concentration, more reactant particles per unit volume, more collisions per unit time, more successful collisions per unit time, a higher rate. So if we look up at the top, which line would be the higher concentration? The purple overlaid with yellow would be the higher concentration. The green overlaid line would be the lower concentration. Why? Because at lower concentration, we will have less reactants particles per unit volume, we will have less collisions per unit time, less successful collisions per unit time, and a lower rate, which means a shallower gradient, a less steep gradient. Okay, pressure. Well, the only state of matter we can mess around with the pressure for is gases. And actually gases, if you look at the picture, it's going to be very, very similar to concentration. At low pressure, we don't have very many reactant particles per unit volume, which is all of that. But at the higher pressure, because we are in a smaller volume, we have more reactant particles per unit volume. So at high higher pressure, we have more reactant particles per unit volume. Same argument. And then the rest of the argument should be the same, and the rest of the argument should sound familiar to you. If we have more reactant particles per unit volume, we're going to have more collisions per unit time, we're going to have more successful collisions per unit time, and we're going to have a higher rate. So again, if we look up at the diagram at the top, the purple line overlaid with yellow is going to represent the rate of reaction at a higher pressure, because we have a higher initial rate, we have a steeper initial gradient. Last one then, surface area. Surface area. Surface area only applies to solids. Now, if we look at the diagram below, we have a large lump of solid, i.e. large particles. Now, large particles have a low surface area. If you think of a brick, you can only touch the outside of the brick, so you can only touch the particles on the outside of that brick. If you cut that brick in half, you can touch all of the surface that you could have touched before, plus you can now touch the particles that are on the surface of where you made the cut. So you can now touch more particles. So the brick hasn't changed the number of particles, it's still a brick, but because you've chopped it in half, with those two half bricks you can now touch more of the surface area, i.e. you have smaller particles with a higher surface area. If you have a higher surface area, and this is very important, we don't have more reactant particles or reagent particles. Same number of reactant particles, if we're using the same mass of something, we have more available. And let's underline that because that's very key. More available reactant particles. And if we have more particles that are available for the reaction, we have more particles we can bump into, i.e. we have more collisions per unit time, more successful collisions per unit time, and therefore a higher rate. So if we look up at the top again, I'll put my little yellow star there this time. If we are looking for high surface area versus low surface area, and this is the last time I'm going to use it so I can write over it, this is going to be the lower surface area curve, which gives us less collisions per unit time, less successful collisions per unit time, and a lower rate, i.e. a lower initial gradient. This is going to be my higher surface area curve. Because if we have a higher surface area, we have more available reactant particles, more collisions per unit time, more successful collisions per unit time, higher rate, and that rate is given by the steeper initial gradient. Now, we do need to deal with catalysts. But that will be in a separate video. I hope this has been helpful. Watch it through a couple of times and then make your own notes on it.